Hi, welcome to the Signal Path. In this episode, I have another repair video for you guys. Now you may wonder what has happened already here. Well, the truth is that I already filmed the beginning of this video once and about 10 minutes ago. And for some reason my camera screwed it up and I missed that and that part's erased and I don't have it anymore. Now I didn't want to close this again and reshoot that part again because it's quite a hassle to put it back together. So I just decided to keep it open like this and just repeat what I said initially during when I first showed the instrument when it was all closed up. So I haven't done anything luckily, so there's no repair attempt being made. I just opened it maybe 2 or 3 minutes ago, so we haven't actually lost anything, which is great. So we can start over. This is an HP 8562B. This is a 22 GHz spectrum analyzer that I just picked up from eBay. And this is a two-banded system, meaning that it has a lower band starting from 1 kHz all the way up to 2.9 GHz, which is treated differently than the upper band, which starts from 2.75 GHz and goes up to 22 GHz. And there's a small overlap between those two bands. So it actually treats the signal that's on the lower band completely differently than it does on the upper band. Now you may remember that this is actually how the Agilent E4407B up there, which I repaired all the way up there, which I repaired in one of my other videos, also works, except that that one does that seamlessly. You don't have to worry about which band you're operating on because it has pin diode switches that automatically switch for you the signal as well as DLO for the converters. This is a little bit different. This is much older, but it's very interesting to look at the architecture of this instrument because you can see clearly how the HP architecture evolved to be the Agilent E-series spectrum analyzer, and then to the PSAs, and now to the PXAs. All of them essentially started from this very architecture. In fact, in my previous video, which I did a teardown of even the older type a spectrum analyzer, you could see the architecture was very similar. So it's very interesting to see this. Now, the way this is built is clearly built to be serviced because this board opens up and then folds down on the table, exposing all of the samplers and the last converters and so on. And even this is in two segments. One segment can be folded up and you can see layer by layer and work on it. This instrument also has a frequency counter, which is done through this sampler over here, and that frequency counter is used because this instrument does not have a Yick-tuned oscillator or a Yick-tuned filter. As a result of that, it actually cannot filter out all the subharmonic conversions of the first converter, so you will see all those tones in the spectrum. And this may sound a little bit complicated now, but it will become very clear once I tell you more about the architecture. So that's why there's a frequency counter, to be able to detect the exact frequency and so on. Anyhow, we can talk about that afterwards. But so far I haven't actually done anything to it. The very first thing I did, I just turned it on, which we missed. I'm going to do that again. And you can see, look at the screen. Unfortunately now the screen is going to be sideways, not the right way up, so I apologize for that. But let's go ahead and turn it on, take a look at it and see what it does. In the front you have a type N connector. I have put a type N to SMA converter here, and this actually has the first LO as an output, so you can use it with an external mixer, which would be quite beneficial if you have subharmonic mixers in the K band and then the 60 GHz band and even higher and so on. You might be able to use. I'm not sure exactly up to what frequency it would support, but it has a very high power LO, so you can use that in subharmonic conversion. And again, this is a super heterodyne architecture with multiple converters and so on. So let's go ahead and turn it on and see what it does. So let's go ahead and turn it on and see what happens. Here we go. So it doesn't really give me much trouble during boot up. We can hear a couple of clicks, but I just want to show you a few little things. So at the beginning it does some LO adjustments, some IF adjustments, and those things seem to succeed because it doesn't give any specific errors. And you can see it's almost done. It's doing different resolution bandwidths, aligning different resolution bandwidth, and it just shows the model number HP8562 and so on and on, and a different revision of the firmware. So everything looks good. I'm gonna go ahead and do a preset. So that click that you heard was the instrument switching to the lower band. So right now this band goes from 1 kHz to 2.9 GHz, and you can see that the noise floor is very flat and it's reasonably low in amplitude, so that seems to be okay. And if I go ahead and change the resolution bandwidth, I can lower the displayed average noise level, as to be expected when you change the resolution bandwidth, because there's of course signal is distributed among more bands. So that makes sense. It looks good. Now if I go ahead and change the the frequency range. So instead of ending at 2.9 gigahertz, I can end at 22 gigahertz. I'm going to go on the frequency, then I'm going to set the start frequency to be 2.75, which is the beginning of the upper band, 2.75 gigahertz, and I'm going to set the stop frequency to 22 gigahertz. And listen to the relay click. Did you hear that? So that was the relay that switched to the upper band. Now, if this instrument wanted to offer a continuous sweep from 1 kilohertz to 22 gigahertz, every time it crossed that boundary of 2.9 gigahertz, it would have to click the relay to the upper position. The relay would be clicking every single time during that sweep, which is of course completely impractical, and this is why they don't offer a single sweep from 1 kilohertz to 2.9 gigahertz. Now, how come other instruments offer? Because they have a pin diode, and here they're using a mechanical relay. For reasons of loss and so on, as I mentioned. So that's the reason why they do that. But there's a couple of other observations here. You can see that the noise floor continuously goes up in discrete steps, and this is because the mixer that's responsible for down converting all the way up to 22 gigahertz down to the to the second converter does it in harmonics of the LO. So this is a subharmonic converter. At the very beginning, it's fundamental, then it's the second harmonic and third harmonic and so on. And that's why the noise figure of the mixer goes up, and that's why the noise floor goes up. So this all is consistent with how this instrument should operate. So it doesn't seem to be anything wrong with it so far. But let's go ahead back. Let me preset this again. Again, you can hear the relay, so it switched back to the lower band again from 1 kilohertz to 2.9 gigahertz. Let me go ahead and put some signal into it and see what happens. So as far as generating a signal within this bandwidth, I'm going to go ahead and use my Rigol DSG3068, which is a 6 gigahertz synthesizer with a built-in IQ baseband generator and so on. It's a dual arbitrary waveform generator built into it, similar to the Ashram one that I have, except more modern, of course. And here I've set the instrument to the lower band, and I'm here at 1 gigahertz and 0 dBm, which is quite a large signal power. I'm going to go ahead and enable the power, and voila, nothing. You can see nothing shows up on the display at all. So I don't even see a tiny signal at all. Now I'll tell you why that is concerning me. Now, since we saw the noise floor change at the upper sideband of the upper band, I know that the LO is present, because otherwise you wouldn't get that noise figure increase in your mixer. You would see more of a linear increase, no discrete steps. So there is an LO present in the system, that we can say for sure, and there's another way to verify that, and I'll show you. So if there is an LO, and if the upper band is working, the fact that I see absolutely nothing here is concerning me, because even if the lower sideband mixer was damaged, I would still expect to see some tiny tone, because no matter what you do, it's very difficult to get absolutely no nonlinearity at all in order to get no conversion at all and see nothing. If I go ahead and increase the amplitude, I'm going to go ahead and go to 10 dB or 12 dBm, which is 16 times more power or so. And where is it? Here we go. 12 dBm. Again, still nothing. At 1 gigahertz, I would expect to see a tone there, but I don't see anything at all. So it worries me, because it tells me that maybe the problem is not just the first converter, but also the second converter, which would be a shame, because now we have two unknowns to fix, and that would be much more difficult. So let me show you another way you can know where the LO is present. Now, no matter how good mixers are, you're always going to have some LO feed through in the mixers. Remember, the lower sideband gets up converted first. So I have to see an LO which would line up to the DC. So if I go ahead in the frequency, and I can say that, show me the start frequency of, let's say, minus 500 megahertz, and stop it at 500 megahertz. There you go. So I'm looking at positive and negative frequencies here, and you can see that this tone right here, that's DC from the way this instrument is trained. Let me zoom in a little bit more, so let me make it more clear. So let me start at minus 50 megahertz. I'm going to stop at 50 megahertz. There we go. So this is actually 0. So you can see that there is something present. That's the LO feed through that's being down converted and shows up at 0 hertz from the perspective of the second converter. So there is an LO. If there is an LO, then that means that I should have seen at least a tiny signal. If I see absolutely nothing, I'm beginning now to doubt the performance of the second converter. And this signal is really low in amplitude. If I put a marker on it, this is sitting at minus 45 dBm. That's really low. So again, this is just my intuition. It's just a hunch that I have, that I think that this is a problem because I see such a low level of signal. And maybe it's not, maybe it is, but we will find out once we look at the architecture a little bit more closely. There's one other thing I want to show you. I'm sorry if it's taking too long, but I think it's important to understand how this works. Let me show you how this instrument measures frequencies above at the 2.9 gigahertz in the second in the upper band, because it doesn't have a Yig tuned oscillator, so you will see all the images of the signal. So as I mentioned, it doesn't have a Yig tuned filter, so I will see all the upper sideband, lower sideband, and all the subharmonic conversions of the mixers themselves. So here I've set the synthesizer to 5.7 gigahertz with an output power of minus 20 dBm, and I'm looking at 2.9 gigahertz all the way up to 22 gigahertz. So let me go ahead and enable the signal and look at all the tones that appear. You see all the different tones that appear there, and let's take a closer look at them and see if we can actually understand what they mean and where they're coming from. Oh, that's going to be a problem. There we go. So let's take a look at these signals. Again, I'm going to enable and disable this RF signal so you can see the difference. There you go, that's without it. You can see all the tones go away, and turn it on and all of them appear. So I expect the 5.7 gigahertz signal to be somewhere around here in the first up converter band. But you can see that I can see the upper sideband and the lower sideband signal, and I can see the upper sideband and the lower sideband signal in the second harmonic, and the upper sideband, lower sideband in the third harmonic, and only the lower sideband the fourth harmonic, because the other one is outside the range of the scope. And you can see the distance between the tones increasing in each band. That makes sense because the LO is multiplied, so the difference between the upper and lower sideband also increases. So this is consistent with how this instrument is supposed to work. It's not, this is actually a good example of how much you should appreciate modern spectrum analyzers that don't, at least as far as I know, this is normal behavior for this unit. But if you don't think, let me know. I've checked and checked, and I think this is how it's supposed to operate, especially because it has signal ID capability. So let's say you're doing this and you want to know, well, how the heck do I know which of these is my signal? Well, this thing has a capability for you to figure it out. Let me turn the marker on first. You can see that I can move the marker around. Let's go ahead and look at the very first tone. And let me see if I can catch it. There it is. So it tells me that the very first tone, I hope you can read this, is sitting at 5.12 gigahertz. That's obviously incorrect because our tone is at 5.7 gigahertz. So that's our first tone. And if I go to the second tone, you can see the second tone is much more close to what I want it to be. There you go. Come on. There it is. 5.7 gigahertz, which is exactly the frequency it is supposed to be. So you can see that indeed there is a tone that matches the frequency of the synthesizer where it's supposed to actually be. And this instrument has a button which you can press to select between internal and external mixers. So I'm going to press it, internal. Now it gives me a couple of options: signal ID to sender frequency, and signal ID being on and off. So if I go ahead and press signal ID at marker, it's going to check to see if this tone is a real tone, or it's an image tone, or it's a tone in the above, in some of the upper bands. How does it do that? If you watch my video of the frequency counter, I did a tutorial on how you can tell what frequency you have down converted based on moving around the LO by a known amount and looking at how where all the other tones move. So you can imagine if I move the LO by a known value, all these tones are going to move around, but they're going to move around depending on the direction in which the LO has changed. So obviously all the upper bands are going to move apart further, the lower sideband is going to go lower, the upper sideband is going to go higher, and so on and on. So you can tell which tone your real tone is by dithering, by moving around the frequency of the LO, and that's a really important concept. So let's go ahead and try that. As again, this is because this doesn't have a filter. Normally, as you move the LO, you would apply a filter, a narrowband filter to the RF. So you would get rid of all the other harmonics that are coming out of your mixer. But this, of course, isn't doing that. Doesn't have a Yig-tuned filter or a very precise bandpass filter that would be able to do that for us. It's not equipped with that. That's why they have this signal ID. So let me go ahead and press the signal ID, and it's going to try and figure it out. Look, it's going to go and it's going to switch around and change things a little bit, jump up and around, and eventually it's going to hopefully figure it out for us. There it is. It's done. You see, it said signal frequency is 5.7 gigahertz and n equal to 1, meaning it's the it's in the first band of n equal to 1. So indeed, it identified the right signal, and it identified where it is supposed to be. And this thing has a frequency counter button, and if I press the frequency counter, you can see that it will count the frequency for me exactly. There it is, it just did it, 5.70000. So the frequency counter is also working. Remember, the frequency counter is in fact a separate piece of hardware, a separate sampler than the mixers. It's a totally different portion of the instrument, so that's also working. You can see that it's changing a little bit around. So there's our signal. Now when I press the internal mixer button, I can say, okay, well, now that we know which frequency it is, move that frequency to the center for me. So now you can see that it has put the frequency of interest in the center, and I can go ahead and change the span. I can reduce the span. There we go. Here's my span is now 100 megahertz, and I'm looking at my signal. So if I change my signal by a little bit around, I'm gonna move it by 10 megahertz. There you go, see, it moves up by 10 megahertz, move it down by 10 megahertz. I'm sorry, by 1 megahertz I meant, and it goes, I apologize again, I meant to say 10 megahertz. So there it is, 5.69 gigahertz, 5.7 gigahertz, 5.71 gigahertz. So now you have a better idea of how this thing actually works. It's a little bit annoying, but that's how this instrument is supposed to operate. Okay, I've turned the unit off. Let's take a quick look at the hardware and the signal path that is somewhere inside the unit to see the different bands and the components that are responsible for the conversion. So you can see a completely through-hole construction here with all the connectors at the edges with a couple of different heat sinks, and this is shielded section. Again, underneath it I think this is the other IF converter, and look, they have a little cutout inside this shield here, the top cap, for them to pass the little cable through. So you can imagine with all the cables running around, this is quite a mechanical challenge as well to make sure everything goes together. Now it looks like someone has already done at least a little bit of attempt to repair this, which is unfortunate, because usually when the unit has already been attempted to be repaired and something else could have gone wrong with it, or that if someone else couldn't figure it out how to fix it, then the chances of us figuring out how to fix it will also be lower. And you can see that they have repaired this cable, and this is the cable that goes into the attenuator. So you can see, I guess it must have been cut or get trapped when this thing was open and closed, so they fixed that. I also see that the cables are cracked. You can see, for example, all the way up here, the plastic has cracked. That's just due to aging. Again, here I have another cable that is cracked. These cables here in the corner, if I bend them, the plastic actually breaks apart because it's so old due to thermal effects over a long time. They've dried out, they've heated up, and are now very, very easy to break. So I'm going to have to think of a way to fix that, perhaps, if we can repair it. And we have to be very careful, because if I bend these cables, these plastic pieces break off. Here you can see here, oh, there you go, another piece of it just broke off. For example, there it is, that piece just broke off from the cable, again, just by me moving it around. So I got to be very careful there. So let's look at the signal path here and follow it. It's actually pretty straightforward. So if you've managed to stay with me up until now, I'm going to try and not talk so much about the circuit anymore and just explain it quickly. So here's the input. The input goes through here. So on the inside of the unit, this is the RF input. The RF input, actually, the very first thing it sees is a step attenuator. So there is a 22 gigahertz step attenuator here. Usually this step attenuators should work with 26.5 gigahertz. So here's our attenuator, and the output of the attenuator then comes out of here and goes into a microwave switch down here. There it is. Here's our microwave switch. So this microwave switch is the segment that selects between the upper and the lower sideband. So let's think about the lower sideband first. So signal comes in through the attenuator, through the microwave switch, comes out of the microwave switch through this rigid cable. This rigid cable goes through a microwave filter. This will filter out all the higher frequencies because they're going to be handled by a different portion of the circuit. So this has a very, very sharp cutoff about above 2.75 gigahertz. And then the signal then goes through this low band dual mixer. So this is actually a dual mixer which handles both the upper and the lower band of this instrument. In the lower band, the signal goes through here and gets actually up converted and comes out of here and then goes into the second converter. So as I said before, the signals from 1 kilohertz to 2.75 gigahertz first get up converted. unlike the signals from 2.9 to all the way up to 22 gigahertz, which get down converted. So the signal goes through here, up converted to 3.9107 gigahertz. That's our first IF. Then it goes through in here, gets down converted down to 310.7 megahertz, and then the 310.7 megahertz signal then goes out to a third converter, which is somewhere on the board underneath this one, which we're not going to take a look at. We're only interested in the first and the second converter. So again, signal going in, attenuator, microwave switch, microwave filter, first mixer up converted to 3.9107 gigahertz going into here, getting down converted to 310.7 megahertz, then going out. What about the signal on the upper sideband? Well, the signal on the upper sideband goes in directly into this mixer and gets directly down converted to 310.7, which then goes through here and then gets fed through this thing again. But then when the signal is already at 310 megahertz, it only goes through a microwave filter in here. It doesn't get converted again, so this is passive at that point, and then it comes back out. So the two signals meet in here, the two 310 megahertz signals meet in here, and they go into the third converter. So that's the overall architecture, and I hope you can follow that. And up here we have an LO distribution network, which just basically receives the LO signal. Here's a Yig oscillator, which is a part of the closed loop in the PLL, and goes through here and then goes in here as an input. Then it splits into multiple 1, 2, and 3. One of them goes in here, which is the LO signal of the dual mixer. The other one goes to the external LO in front of the instrument, and the third one goes back down in here, which then goes into the sampler for what I think is the frequency counter. So that's the overall architecture. Now, what is most likely damaged is this first converter of the lower band, because the upper band is working. This thing is able to down convert to 310.7 megahertz. That part is working, but the up conversion to 3.9107 gigahertz is not working, and that's why we are having a problem. But that's easy for us to find out. We're going to disconnect this and look at this signal directly. What do we expect? We're expecting a signal to be up converted to 3.9107 gigahertz. So that should be pretty easy for us to find out. Now you may ask, well, if there is only one LO input, how does this switch between the two LOs? Because down here we switch between the two RFs using a microwave switch. Well, this dual mixer actually has a pin diode that it uses to switch between the LOs. They don't use a pin diode for the RF because that's going to be significantly more nonlinear. They don't care so much about the LO, but they will care about the RF, and they will care about the losses and so on. So they're using a microwave switch for the RF, a pin diode in here for the LO. And yeah, so what's the first thing? First thing is let's disconnect this, hook it up to the spectrum analyzer and another spectrum analyzer, put in a signal and see if this thing is actually working or not. And I recognize that this is probably it's an advanced repair really, because I'm not going into a lot of detail, but if I did, then the video would be 5 hours long. But I hope you're following me, and if you have any questions, post them, and there will be a lot of other helpful people to help you, and I'll try to answer as well. But first thing to take a look at is the dual mixer, and I have a anti-static strap here, which I'm going to hook myself into, because these things are very, very ESD sensitive, these components, so you have to be very careful when handling them. There we go. I did a quick search on the internet, and indeed I found the block diagram, and it was exactly like I described it. So I didn't have this before. I should have looked a little bit earlier, but here we go. So here is our input, anywhere from 1 kilohertz to 22 gigahertz. It goes through the step attenuator, then it goes through a microwave switch. The low band, which is from 1 kilohertz to 2.9 gigahertz, goes through a filter, just like I showed you, and then it goes into the dual mixer. In one of the two mixers inside the dual mixer package that I was going to take a look at. And here you can see that there is a selector where the LO is selected between one or the other. Here's the LO distribution amplifier. And the LO distribution amplifier has an output that goes outside of the instrument, and then it has another output that goes into the dual mixer, and it has yet another one which is not which is shown here, and this one goes into the RF assembly for the sampler that was there. So these are the three outputs, and here's the LO being selected using a pin diode between the two mixers. In the first mixer, it's up converted to 3.9107 gigahertz, which then goes into the second converter, and the second converter has a ×6 multiplier built into it, so it receives an LO of 600 megahertz, which then gets converted to 3.6 gigahertz. And the difference between 3.6 gigahertz and 3.9107 is 310.7, which is the second IF of the second converter. So you can see that in one path we are going through here, and the other path we are going through here. And the second converter acts as simply a pass-through when you're in the upper band. It doesn't have an amplifier, so the second converter does not have another conversion in it. And then the third converter, which is somewhere inside the board, which I'm not showing, gets another LO from somewhere else, and again you can select back and forth. And I'm not going to worry about this section of it because it's not something we're looking at, but I've covered quite a bit of this material in the past, so hopefully it's straightforward. So the suspect component is here, and I am going to take a look at this signal right here. If this signal is not up converted to 3.9107 gigahertz, and if it's not strong enough, then this component is dead. But out of this component, I know that only this one is dead, and the other mixer is working because the upper band is working. So this path is functional, this path is not. My concern was that not only is this dead, but also this is dead, which then would be a bigger problem because I saw a very weak LO and I saw absolutely no signal coming through at all, even with a very large signal, because I know the LO is present in the first dual mixer. So I hope this helps a little bit at least, and now we can go ahead and take a measurement and see what it does. Okay, so what I've done here is I'm taking the output of the first mixer, the output that's up converted to 3.9107 gigahertz, and I'm going to look at that on my other spectrum analyzer. And what I expect to see here is not just the LO feed through, but also an up converter signal. Right now the instrument is sweeping, and look, I do get, in fact, there we go, I see some LO, jumping around because the instrument is sweeping. Is to be expected for the LO to not be stable in one location. So what I'm going to do is I'm going to set this spectrum analyzer to 0 span. So it will only be at a single frequency, and the LO will not move around. It will allow us to be able to decode it. And look, just as a side point here, look. You can see here, here's the LO of my instrument, the other Agilent one. You see how this is the LO that I was showing you in the other one? That's how I knew that the LO is present, because this one is obviously working. You can see, look, there we go, that's at DC. That's our LO feed through from the first converter. Anyhow, some little tips here and there for some advanced repairing. So let's go ahead and set the instrument to 0 span, and I'm going to set it to 0 hertz. That's going to then force it to have exactly the LO that's listed. I don't think I showed you a close shot of this, but here it is. See, it's written here that the LO is indeed, it should be the up converted to 3.9107 gigahertz, and the high band gets down converted to 310.7 megahertz. And you can see this bias voltage is written here. The instrument actually automatically changes the mixer bias voltage depending on the harmonic of the LO in order to minimize third order IM3 distortion products. This is a really, I shouldn't call it ghetto, but a really ghetto way of doing it. Basically, they're calibrating it in advance for the lowest distortion depending on the LO of the harmonic of the LO. Nowadays, it's all done digitally and so on. But anyhow, that's how it's working. So I'm going to go ahead and set it to 0 span, and if I do that and I set it to DC, I expect this tone to stop jumping around as it is. So frequency, I'm going to set the span to 0 span, and I'm going to set the frequency to 0 hertz. Let me see, 0 span. Is it doing that for me? There you go, span equal to 0. There it is, it's doing it. Look, it's not moving around anymore. And what do I expect this frequency to be? Well, if everything is working, this is the LO feed through, which by the way is enormous. So there is definitely something going on. You shouldn't have this much feed through in a circuit. So let's put a marker on that. I'm going to go peak search, and you can see the amplitude is 1.3 dBm. And again, this is just the LO feed through. That's really big. And the frequency it's reporting is 3.92 gigahertz. The reason it's not 3.9107 is because the span on this instrument is really high. So I can go ahead and change that. Let's go under center frequency of this and set it to 3.9107 gigahertz. That's our span. I'm going to change actually the sender, I'm going to change the span to a much smaller value. There we go. Now the span is 50 megahertz. Now if I do a peak search, there you go. You can see that exactly 3.9107 with a lot of zeros afterwards. So it's exactly dead on. So there is no problem there. I'm going to reduce the resolution bandwidth even further. Nice, beautiful, clean tone. It's just gigantic. Now At the same time, what I've done is that I also have connected a signal to the input, which will then go to the mixer. So I'm going to use the Rigo synthesizer. I'm going to set the Rigo synthesizer to 10 megahertz. So then I would expect the 10 megahertz to get up converted around a 3.9107 gigahertz carrier, and I expect to see my up converter signal sitting right around this tone. I actually haven't done this yet, so let me see what happens. Here we go. It's going to be just as much of a surprise for you as it is for me. There we go. Oh, look at that. They're there. They're right there. They're just really, really small, which means that this mixer is undoubtedly completely dead. There we go. So you can imagine, obviously this mixer isn't working, because here's my lower sideband up converted, here's my upper sideband up converted, here's my LO feed through. The LO is sitting at 1.123 dBm, but my my up converter signal that I'm interested in actually looking at is sitting at minus 60 dBm. No wonder you don't see anything, because this, but remember what I said? I said that no matter what, even if it's completely broken, there will be some nonlinearity you cannot avoid, and this is what I was talking about. So the fact that the instrument doesn't display this tone at all is what was concerning me, what was worrying me, because if this tone is there, I was expecting to be able to actually observe that when I looked at this instrument in here, because this signal then goes into the second converter, and that converter would convert it back down to 310.7 megahertz. We know that the 310 megahertz system works, because if it didn't work, the upper sideband wasn't working. So now I have two suspects. First of all, I know for sure that the first mixer is broken. That's first problem. The second problem is that I'm not confident that the second mixer is working. So let me explain that again using the block diagram, because I'm sure that some of you are confused. So let's go ahead back here. Oh, sorry about that. And let's take a look here. Okay, there we go. Sorry, I get excited and I forget to turn the camera on and off. But there you go. So there's the input. I just confirmed that this mixer is dead, because the signal looking at here has barely any conversion gain. It's sitting at minus 60 dBm when the signal at the input at 0 dBm. So it has a 60 dB up conversion loss, which is dead. There's no way a mixer would be that bad. But then the signal goes in through this mixer. I would have expected this mixer to at least show me something, even though this signal was so small, because I would have expected this to perform better. I could be wrong, but anyhow, I'm going to take a closer look. So we can look at this module too, since we know this module is for sure dead. And then we know that this path is working because we can see the upper sideband, so I'm not worried about this portion of the circuit. I'm only worried about this mixer and that mixer. Now, because the LO signal, LO feed through from here to here is so huge, I'm worried that the 1.1 dBm signal feed through into this mixer actually has damaged this mixer over time. So that's another reason why I would think that both of these are dead. So what I'm going to do next is I'm going to do a quick search on eBay, just out of curiosity, to see if I can find a replacement part for these. Because if I can, that would be easy. We'll just change the modules, because these things aren't really repairable, because they are they're not quite monolithic, but they're hand assembled individual components and die and wire bonded, old technology, so you can't really repair them. So let's see if if I can get a replacement component. Well, there is good news and there's bad news. The good news is that I found a replacement part for this, even though I'm not 100% sure it's broken, but I found it for only 40 bucks. And I bought it, which was just really cheap. And I mean, for $40, I have no problem. This unit is worth much more than that. But the replacement part for this was about $500, and I wasn't going to buy that because I have another idea. Somewhere else I was investigating what else we can do. There is another way maybe to fix. I have another idea which I'd like to try for this one. But I have found a replacement for this. So I suggest let's just take a big risk and replace both of these at the same time. I'm gonna go ahead and take this, but when I replace this, I'm not going to connect this mixer back to it, because it has such a large LO feed through. I'm afraid that it's going to damage the new one that I've bought. So I'm going to remove this, put the new one in there, and I'm going to then do what I think can be done to fix this by bypassing it and doing some other stuff, and I'll explain that, and then we'll put it all together, and then, well, it's a shot in the dark, but hey, that's what we're going to do. Let's try and see if we can fix it like that. So I'm gonna wait for the parts to arrive. Alright, guess what has arrived? I've bought two things which I think are going to help repair it. First was a second converter replacement, which is in here. I'm not going to touch it with my hand because this is very EST sensitive component, and they've done a nice job unpacking it. You can see they've put some protection there for the pins not to bend, so we can go ahead and remove it from the old one, and then when we remove it we can actually take it apart and look at it under the microscope. That will be fun too, to see what's inside it. So there we go, so we can put that aside. But I've also bought a mixer from Mini Circuits. This little mixer is passive, and I'll show you the data sheet, and it covers all the way up to 7.4 gigahertz. So I can use this to upconvert the RF signal at the input all the way up to the frequency that I needed to be, which was, I think it was 3.9107. So I can replace the first converter with this one. The second converter stays where it is, but now I'm going to have to switch the LO between this one and the mixer that was there, and I have a way of doing that. I have a microwave switch which we can add. So there's some construction that's going to happen. And now, of course, once I change the mixer, the conversion gain is going to be a little bit different, and the instrument is going to require calibration. But hey, that's one way to do it. We're doing this for fun anyway, so we can see if this method will work. So first thing first, let's go ahead. I'm going to go ahead and let me turn this around. This thing has been sitting open on my desk for some time now. So I'm going to remove that, replace it with the one that I just bought, and I'm going to then remove some of these cables and rewire it, and basically replace the mixer with the one that I just bought. So let me show you what I mean exactly on the block diagram. There you go. So I have bought a replacement part here because I suspect this mixer was bad. So we're going to replace that, and I'm going to replace this mixer with the external one from Mini Circuits that I bought. But because the LO goes into this module, I'm going to have to move this from a pin diode to an external switch. You know how there's a microwave switch in here? Well, I plan to use another microwave switch and put a microwave switch out in here, where I can select the LO to either go into this path or go into my little mixer that I bought from Mini Circuits. By the way, this was, I think, also about $50. So far I've spent about $90 in attempt to repair this, which isn't so bad. So let's go ahead and do that simultaneously. Remove this from the unit, put the new one in there, and then remove this pad, put get a microwave filter, connect it all up together, and then voila, magic's gonna happen. Let's see if it works. So I went ahead and I removed it, and I just found another nail in the coffin, and that this thing is probably also damaged. First of all, it was missing a screw, so the screws are in here still. You see there's two on this side, but there was only one on this side, so there's a screw missing. And the other thing I noticed is, look, if you look carefully here at this component, which is I think an op amp or a comparator, there has been some work done on this. So this is either damaged, or someone tried to fix it, or they couldn't fix it, I don't know, but either way. So now I've taken it out, and there's two resistors in here which I suspect are for calibration of something, which of course are not going to be the same for the one that I bought, but again we have to go and see what we can do. So the one that I have purchased for a very good price is supposed to be working. It is labeled as working, and look, it even still has its calibration sticker, which of course this one did not. So this will be another good one. And let me see, and here you go. Yeah, I see even has a seal here. This one also doesn't have a seal, so I guess someone's opened it, but the value of the resistors are different. To be honest, not 100% sure what these resistors actually represent. Probably some biasing again of this component. So there's a little bit of an unfortunate thing there where we don't know, but so the conversion gain might change. I'm hoping that the conversion gain of the upper sideband of the upper band wouldn't change, because it's only passive for the upper band and active for the lower one. So I'm going to go ahead and install this, and then we'll turn our attention to figuring out how to get rid of that second mixer. So there's a couple of things we can do to see if my idea would work at all. So here I have the external mixer. Remember that this thing provides an LO out, and that LO out is coherent to the same LO that goes into the mixer. So if I take this LO out, it'd be like taking the LO from this one. Then I'm connecting that to my external mixer's LO, and then I'm actually directly applying from the synthesizer the signal, which would be my RF signal. In this case, it goes into the IF port of this one, and then I'm taking the RF out and I'm looking at it on the spectrum analyzer up there. This setup is identical to what I was doing before when I was looking at the signal coming out of this one, because now I've replaced one of the mixers in here with this mixer, and let's see if it works. Remember that when we did this, we saw an LO feed through that was huge. It was like 1.1 dBm. And now I'm doing the same thing. I've done the same thing. The instrument is set to 0 Hertz, a 0 span, so I'm expecting to see the same LO coming out, and then I'm going to turn that on. But take a look at this. Check it out. So I do see again, oh, let me see if I can get this thing to work. I do see again, as before, my LO coming out of the instrument, but the LO is much smaller. So if I go ahead and do a peak search here, you can see the value of the LO feed through is now about minus 17 dBm, which is much less. And now if I go ahead and apply a minus 10 dBm IF signal, like so, you should be able to see the up conversion happen. There it is. Here's the lower sideband. There is the upper sideband. Now if I move my marker around, you can see that I am getting a signal of, if I can get this thing to stay, my goodness, why can't I do this? There it is, minus 20.6 dB. The signal I'm putting in is about minus 10. The signal I'm getting out is about minus 20, so it has a minus 10 dB of up conversion gain. The other mixer had a minus 70 or minus 60 dB up conversion gain, which was, of course, was broken. So minus 10 dB up conversion gain is reasonable. I think it's within the data sheet of that part. I promise to show you the data sheet. I haven't forgotten. I will go ahead and do it. So this is the first step to see if this method would work. The next big step would be, let me put my anti-static thing back on here. The next thing would be to connect it directly in here. Remember, this used to be connected to this. I've replaced that, so now the output of this mixer will have to go in here. And then I should be able to see it on the screen. If I see it on the screen, then essentially we can say that this repair is possible, at least. And then after calibration, it will be amplitude leveled. But I'm going to try that. Before I do, let me just quickly show you the data sheet of this, just so that we can make sure we understand how it works. And here's the data sheet for the mixer I'm using. This is the mini circuit ZX05-U742MH Plus, and this is a 0.1 to 7400 megahertz mixer. It requires an LO power of plus 13 dBm, which I believe is within what I can get from inside the instrument. Now, if you look at this, look what it says right here. The conversion loss is listed as, where was it? I just saw it. There you go. The conversion loss is listed somewhere between 8.3 to 9.9, and I just measured it to be about minus 10, which is very close to this. So I'm confident that this is working, and you can see there's a whole curve showing the conversion loss and so on. Of course, this has to be calibrated because the instrument doesn't know the conversion loss versus frequency. So this might pose an issue later for calibration, but that's we'll worry about that later. And you can see the architecture is a double balanced passive mixer where the LO and the RF are both going to a transformer becoming differential, and the LO and the IF is taken out from the center tap of the transformer on the RF side, which is a very typical configuration with the diodes like this, passive mixers like this all the time. And of course, because it's passive, it requires no power, but it has higher conversion loss and all the good stuff about mixers. So a nice double balanced mixer which we can use in the place of the one that's internal, that's broken. So let's go to the next final step, well, the semi-final step, and connect directly the output of this to the second converter and see if the instrument will actually detect it. Here we go. So what I've done is I have essentially completely bypassed this mixer. Now I'm taking the input to the mini circuits mixer directly from after the filter, like it used to be. This used to go into this mixer, now it goes into this mixer. The LO used to go to this one, now it goes to my mixer. And finally the RF coming out of the air is now directly going to the second converter. It used to come from here. So now I've done all of that, and if you take a look at the screen, it has a bunch of other tones that now show up there. I wonder if that's again normal behavior because it doesn't do proper filtering, but check it out. I have 1 gigahertz signal here at minus 10 dBm, and when I enable that, voila, there it is. And if I were to put my marker on it, I can, there it is, I can measure it, and it tells me the amplitude is minus 12.5. Remember, this is not calibrated, but minus 12.5 is actually really close, because I have some losses in this cable, of course, and I have a whole bunch of losses in these cables, which are quite high because they're very long, and so on and on. So, you know what, once I change those cables to better cables, it might actually be dead on. At least at 1 gigahertz it will be dead on. So it seems like the conversion loss of this mixer, the mini circuits one, is really comparable to the one that used to be already in the unit, and whatever the difference between this mixer is and the one that used to be in there's the second mixer, whatever it is, either the difference is small or it all works out at the end just by luck, I guess. But the other tones that are in there are a little bit puzzling, because I'm not 100% sure where they're coming from, because it's the LO tone is very pure. So even when I have no signal at all, I still have those tones. But when I disconnect this mixer from the second converter, you can see that they indeed disappear. So they are being registered somehow from this first mixer. I am not, to be honest, 100% sure if this might even be normal behavior for this. I don't know. This is a weird spectrum analyzer that doesn't have the proper bandpass filters in it. But anyhow, nonetheless, we can figure that out perhaps later. But what I'm interested in is finding a good way of putting this in here, because right now I actually I'm not able to really use this instrument in the upper band anymore, because I have disconnected the LO. Of course, we can't leave it like that. We need the LO in here, because for frequencies above 2.9 gigahertz, I still need to use the second converter. So I've disrupted the signal path for the upper band, which of course is unacceptable. So I'm going to go ahead and find a way to put it all together. I have a couple of ideas, and let's see if that works. So I've put together this little module, and this module is nothing more than the mixer that I already had, plus a microwave switch. This microwave switch is at the same voltage configuration than the microwave switch that's already in there, so I can drive it from the same driver that does the RF switching. Now that's very convenient, because since I already have a relay driver built into the unit to switch between the RF between the upper and the lower band, I can now use this microwave switch to switch the LO between the upper and the lower band as well. This way I can feed the LO in the middle. Then when I want to use the lower band, the LO is fed through this line to my mixer, and when it's on the other side, the LO is fed through out of this one at the output to the other mixer. That way I can have both functionalities, both bands at the same time. So this is kind of what I constructed as a result of that, with a bunch of cables. And I'm going to do my best. I don't have enough rigid cables, and these things are very difficult to bend in place. Anyway, so I'm going to try and there's the inputs, by the way. You put 28 volts in here, it will switch to one side, and when you let it go, it will by default be switched to the other side. So that's what I'm going to use. I'm going to try and fit it inside the unit, and then hopefully when it's all together, we can give it a test and see if it all works. Alright, here's our final product. So I have placed everything inside, tucked away as neatly as I could. I did it in a little bit of a hurry, but nonetheless, here's the microwave switch that I installed. Here's the mixer, and you can see that I wired it up with the blue wires. Those are actually pretty good SMA cables, so I'm not quite happy about leaving them inside the unit, but it's okay. So then here's the power cable for the relay, and I've tapped that off here from the same cable that powers the main microwave relay, which switches between the RF input and output. There's one cable still missing I have to install, which is the cable that carries the final the RF back to the other mixer, so I have to still install that. So imagine that this is sitting here, and then everything else is done. So what I'm going to do is I'm going to close it up as well as I can. Now I also actually found the replacement cable for this one that had that was broken, that the pieces were coming off. I put some tape on it, but I'm not very happy about the tape, so I'm going to go ahead and use this cable as a replacement, which is very similar. It's the same length and everything, so you should have similar losses, and hopefully it will be fine. So then that's about it, and you can see that I'm taking the LO from the top, goes into my microwave switch and comes back into the other mixer, and so on and on. So everything is nicely wired up based on what I described before. And actually I was just looking at this. This is the other mixer that I took out, and at the bottom of it, it actually says bad. I'm so annoyed, which means somebody has already taken this out and putting it back together and so on. Anyhow, so I'm going to go ahead, close it up and we'll do some tests on it and see what happens. And I'm curious about what you guys think about the extra harmonics that show up. I'll show you in a moment. Here we go. So I've put the unit back together. Right now I'm looking at a 5 gigahertz tone, and you can see that the upper band is working perfectly like it was before, and there's a single tone in there at 5 gigahertz, and I can move that tone up and down by about 10 megahertz or so. Let me see if I can do that. There we go. Oh, I did it too much. That was 100 megahertz. There we go. There it is. So 10 megahertz up, 10 megahertz down. So it is indeed working, and I can go ahead and do the same thing and now jump to the low band. So I can go under frequency and I can set the center frequency now equal to 1 gigahertz, like so. And I can go ahead and enable the frequency at 1 gigahertz. There it is, and you can see the tone at 1 gigahertz. And again, you can see there's some spurious tones around there that are the result of this repair. Unfortunately, I'm not 100% sure why it is happening. Perhaps there were some built-in filters that used to be available when the internal unit was installed, when the internal dual mixer was working, and because it had a diplex, right, its output probably was some filtering, and that filtering is not available, so you get some spurious tones. But it's okay. It's still, at least now you can look at some signals between DC to 2.9 gigahertz. And again, this repair is just an exercise for just to learn something new, and I have something to take apart and show you guys. Not really didn't want to spend too much time trying to figure this out, but hey, it would make a very good, exciting discussion on the website where we can talk about what the potential cause of those are, perhaps coming from the LO and the way it's going through the external mini circuit mixer, and there might be some harmonics and some tones and some self-mixing that shows up at the frequency, RF frequency, where it shouldn't be, and then it gets detected because it's not properly filtered. But anyhow, it would be interesting to talk about it, but nonetheless it's now much more functional than it was before, and it works. So now you can look at signals from 1 kilohertz or so all the way up to 22 gigahertz. I hope you enjoyed this repair. I'm gonna probably put this thing back on eBay. Don't really need another very big spectrum analyzer here in the lab, but if you liked it, please make sure you give it a thumbs up, and I will have some more interesting videos in the future. I have a whole bunch of reviews and a whole bunch of tutorials I'm trying to prepare, so stay tuned.